All right, so hello everyone. In this video, we're going to discuss how you can check your work using dimensional analysis. And you can actually use dimensional analysis for all sorts of things, but one of my favorite ways is when you have maybe some lengthy calculation that you're doing with a lot of algebraic, manipulations, and then you get to some final answer and you don't really know if maybe you made a mistake. Did you drop like a power of 2, or did you divide when you meant to multiply? And so using dimensional analysis is a great way. It won't tell you 100% if you were right, but it at least will tell you if your answer is even physically possible. So in order to get started, we need to make sure we all are on the same page about what we mean when we say the word dimension. Now, a lot of people know that maybe it's sort of related to units of your variables somehow, but it's really quite a distinct concept. It's related to units, but it's distinct. And I think the easiest way for you to understand what I mean when I say dimension is just by looking at some examples. So what we'll do is let's consider some variables that we might want to measure. So we'll look at some variables. And then we'll consider what units we might use to measure these variables. And then finally, what is the dimension of the variable, and how is that different from units? So for instance, maybe you want to measure the height of a tree. So we'll start with height. We could represent this by the letter h. That's our variable that we might, do some calculation with. And what are units we could use? If we're measuring the height of a tree, maybe the meter, maybe miles, maybe kilometers. You really have a lot of choices in what units you use when measuring the height of a tree. But what is the dimension? Well, the dimension of this variable height is length. So this is often denoted by the fact that it has a dimension, uppercase L, which stands for length. Now, what's something else we might want to measure? Well, maybe you drive a certain distance and you want to measure the distance you drove in your car. So we have some distance. And maybe we'll use the letter D as our variable. Again, we could measure this using meters, miles, kilometers, really the same set of units. And this is telling us that distance traveled in your car also has dimension length. And again, you can tell that by the fact that you can use the same set of units. And either way, if you're actually making that measurement, you choose a unit, but it always has to be some unit of length. And then finally, maybe radius. And we would use the letter R, and hopefully you already guessed, yes, a radius is also a length. You can use meters, miles, kilometers. So let's move on to something different. Maybe you measure the mass of that tree or the mass of your car, letter M. Now we have a different set of units. We would use kilograms, grams, whatever unit of mass you like. And so this has a different dimension, denoted by the letter M. Maybe you measure the time it takes to drive from your house to the grocery store. Lowercase t for our variable, seconds, minutes, hours, days, whatever you like. This again has a different dimension of time. And so these are it'll turn out that length, mass, and time are the primary dimensions that we'll have for our variables in your introductory level physics class. Eventually in Physics 2, you might get up into things like charge or temperature, but really in Physics 1, length, mass, time will be our main dimensions. But we could consider more complicated variables like velocity. Or really, I'm just thinking about the magnitude of velocity, the speed. The letter V. Now, even writing the units that we might consider, we'll see that this gets more complicated because we have things like meters per second, miles per hour, etc. And so if we want to talk about the dimension of velocity, this turns out to be length over time. So generically, whenever you measure the speed of any object, again, you can choose whatever unit you want, but it always needs to be a length divided by a time. So hopefully you're getting the point here. Maybe we'll do one more complicated example. So maybe we'll use a density. and really a volume density, which is often denoted by the Greek letter rho. This is not a P, it's a rho. And so this is a mass divided by a volume. So units might be kilograms per meters cubed, or I don't know, grams per miles cubed. That would be a real interesting density to choose, but you could. But again, it's always going to be a mass divided by a length cubed. All right, so now hopefully you're getting a feel for what I mean when I say the word dimension. Now let's think about how this can help you to get the right answer, especially like in an exam type setting where you're kind of stressed, you get this final answer, you really want it to be right. Using dimensional analysis to check your answer is a great way to help you, score some extra points on your exam. Okay, so if you did some complicated formula, let's maybe start with an example of a simple formula. So let's consider, maybe you just want to compute again that distance that your car travels. It's moving at a constant speed for a certain amount of time. So let's say you want to know the distance you travel at a constant speed. I'll represent that by the variable v. We don't know exactly what that speed is. It's just some variable. And you drive that for time t. And you want to compute this distance. And so maybe even dimensional analysis is also a way that I use to just help me remember formulas. So you say, okay, d, and you're like, it's some combination of this velocity and time. What combination could it be? Is it v times t, v divided by t? I don't know. So it turns out that it's v times t. And how do you know if you're right? Well, if you had actual values, you could plug them in, and you would say, oh, if I multiply 30 meters per second times 20 seconds, I get out something with units meters, which is a distance. That's good. But sort of more generically, if we want to see if this is an equation that even makes any sense at all, what we can do is take the dimension of both sides. And usually we do that by these square brackets. So this is saying the dimension of the variable d, and on the right-hand side we have the dimension of this quantity v times t. Now it's really easy. We want to sort of break apart this right-hand side. The dimension of the quantity v times t is happily just the dimension of v times the dimension of t, the easiest possible thing. And now we want to go up to our list of our dimensions for all of these variables. The dimension of v, velocity here, we have is a length over a time. So this is L over capital T. And then time, of course, has the dimension of time. And then maybe let's use a different color. These little guys cancel out. And we end up with a length. And that's what we would expect for the dimension of a distance. Now maybe again, so maybe you had forgotten the formula or made a mistake and you tried velocity divided by time. Let's try that. So let's actually see. So wrong thing to do is if we had done, let's say you thought, oh, maybe distance is velocity divided by t, and you're like, is this the right formula? We take the dimension of both sides. So again, this is just the dimension of velocity divided by the dimension of time. And then we would end up with length divided by time, which is length divided by time squared, which is not the dimension of distance. And so you would find out that is a big mistake. That's a big no-no. You must have made a mistake in your calculation. And here it is that you accidentally forgot the equation for the distance when you're driving at a constant velocity. So don't do that. So let's do one sort of complicated example. And I'm going to ask you actually maybe to pause your video and try to work out the dimension of this quantity for me to see that we're on the right page. So maybe let's try, what is the dimension of the function? Let's do some mass divided by some density, some radius, and some height. So what is the dimension of this? And now pause the video and try it on your own. All right, so let's do it together now. So again, this is just the dimension of mass divided by the dimension of density, dimension of radius, dimension of height. This is just, this is just mass. Dimension is just mass. Density dimension is, again, mass per length cubed. So we end up with a mass on bottom. That length cubed ends up on top. Radius is length. Height is length. And so we get these masses cancel. And then lengths cancel with two of these three lengths. And we end up with a length. And so I don't know what this is a formula for. I just made up this formula. But maybe this was a formula for a certain distance. And then you did this and you find out it has dimension of length. So this is a reasonable formula for, maybe it was your height of the tree. I don't know, whatever you're trying to compute. So whenever you calculate anything on your homework, or especially on an exam, I highly recommend you go through this process. It'll really help you find if you make any little mistakes. Again, you just divide when you meant to multiply, you drop a power of 2. It'll really help you to find those. And I guess the one last takeaway point I want to mention, which I didn't say, a lot of times functions that you might calculate have like factors of pi or a factor of 2 out in front. So a final question is, what do you think is the dimension if I had multiplied this by the number 3? All right, that's a wonky 3, but the number 3. How do you think that affects the dimension? Well, it turns out that the pure numbers are dimensionless. So numbers that don't have any units, like the number 3, don't have any dimension. So I could maybe add a little dimension 3 here, but the dimension of 3 is just nothing. So it doesn't affect anything. You can multiply this function by any number, still the dimension of length, any pure number, that is. So hope that helps. Enjoy.